Hey everybody. So we're going to talk today about an idea called expected value. So I'm going to start explaining this by use of an example. Okay. So suppose that we were to conduct the experiment. We're going to roll a six-sided die. Okay. Now, I might ask you the question, what am I expected to get when I roll the die? And there's not really a good answer to that question. We expect each value on the die to come up, has an equally likely chance of coming up, right? Each side has a 1/6 value. Excuse me, 1/6 probability of landing. However, what if I ask a slightly different question? Imagine I conduct this experiment 600 times. What do we expect to happen? And sorry, what do I think my average roll will be, right? What do I expect the average to be over 600 rolls? So let's pretend for a second that things work out perfectly and that we know that each side of the die has a 1/6 likelihood of landing. So if I rolled it 600 times, I might expect to get 100 times, 100 times, 100 times, and on up to 100 times. Okay. So now let's pretend that happened. I have a list of data of all the rolls, and the number once was rolled 100 times, 2 was rolled 100 times, and so on. And I'm going to compute the average. So what do? I add up 100 times. I add up 100 times. I add all those numbers together and divide by how many times I rolled the die. So what would that look like? Well, I would have 100 rolls. Let's use some notation. Our mean, I would have 100 rolls times the number 1. That would be like adding up all the number ones, plus 100 rolls times the number 2, plus 100 rolls times the number 3, 100 times 4, 100 times 5, 100 times 6. And then I would divide this by 600, right? So that's like adding up all the ones, that's adding up all the 2s, all the 3s, all the 4s, and so on, and then dividing by 600. Okay. Now, we could just plug this into a calculator, but I want to compute it slightly differently. I'm going to use a little bit of algebra here. I can separate these into different fractions. So I have my first fraction is going to be 1 times 100 over 600, plus 2 times 100 over 600, plus 3 times 100 over 600, plus 4 times 100 over 600, plus 5 times 100 over 600, plus 6 times 100 over 600. Okay, again, I'm not doing this because it's easiest to compute this way, but I want to show us something. And then I can write each of these fractions in the following way. 1 times 1/6, plus 2 times 1/6, plus 3 times 1/6, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. Okay? So again, I could have computed it on the first line, but here's something I want us to hold on to. Now I'll compute it. It turns out to be 3.5 would be the average of this sample. If I did it 600 times and it worked out this perfectly, this is the average we would get. Okay? Now, this is something we call expected value. Okay? It is what we expect to happen if we perform an experiment many times, right? It's related to an idea we mentioned in the beginning, the law of large numbers, that as we conduct an experiment, the more we do it, the more it tends towards the theoretical probability. For instance, when we flip coins, if I flip a coin 4 times, I might get 4 heads in a row. But if I flipped a coin 400 times, I'm very unlikely to get 400 heads in a row. I'm probably going to get something very close to 200 heads and 200 heads. or 200 tails. If I flip that coin 20,000 times, I'm more likely to get even closer to 10,000 heads and 10,000 tails, half and half, right? So the longer we do it, the closer we expect it to get to the frequency that we expect, okay? That's part of the notion behind expected value. Sometimes we call it the long-term average. So before we write that down, I want to notice something. Let's connect this thing to a random variable. So notice, let's make the random variable x is the number rolled on our 6-sided die. Okay. I'm going to make a frequency table, probability distribution for this random variable. We'll list the values of x and the probabilities of each of those values, right? So in this case, there are 6 possible values, the 6 numbers we could roll. And each of them has a 1/6 chance of being rolled, right? Well, notice what we did here. If you look at this line here and compare it to this chart over here, each term in this sum is the product of the value on the die times the probability of it happening. The value of our random variable times the probability of it happening. In other words, if we take x times the probability of that value, right? If I multiply this across, I get 1 times 1/6, 2 times 1/6, 3 times 1/6, 4 times 1/6, 5 times 1/6, and 6 times 1/6. If I add those up, that's where the 3.5 came from, okay? And so this is our little clue as to why this is going to be our definition of expected value. When we have a random variable, what we can do is we take the value of our random variable times the probability of that value. We do that for each value. We're dealing with discrete random variables here, and we sum them together, okay? And when we sum them together, we get what we call the expected value. So let me write that out. We will say the expected value of the random variable x is, so we use a symbol E of x. We also use the symbol mu. Remember, this is the same symbol we used for the mean of a population. And we use this here because it's related. This is like a mean, and it's the one way to think about it, it's the mean over all time. If we did whatever experiment we're doing forever and ever, or over however many instances are possible, this is what we expect the true mean to be when we take the entire population of events or trials of whatever experiment we're conducting. Okay, so we write this using what we call summation notation that we've seen before. It's a little bit still probably pretty new to most of us. So this is our Greek letter sigma. It just means add up all the things that come after. So what we're doing, so sometimes we notate it this way: x sub I is each individual value of the, or is an individual value of the variable x. And we multiply each individual value times the probability of that individual value, right? So forget the summing. This just means take one of the values of our random variable, multiply it by the probability of that value. Then this says do that for each of them and add them up, right? Which is just what we did here. I multiplied the value 1 times its probability, right? It just so happens in this case they're all the same probabilities. That doesn't need to be the case, but we multiply them all together and sum them up, we get our expected value, okay? That is how we compute expected value. Often there are some tricks that we'll come upon in certain cases, okay? This tells us what we expect the long-term average, the long-term mean of X to be, right? In the case we just did, it's rolling dice, but it could be for any, right? If we had a random variable, how many students show up to office hours each week, right? If we could understand that probability distribution, if we had all of the values and the probabilities, we could come up with an expected value so that I would have a notion of how many to expect each week, right? Doesn't mean that many will show up. Just like in the case we just did, we will never roll a 3.5, right? But sometimes we'll roll 3s, sometimes we'll roll 4s, and they'll average to 3.5. Sometimes we'll roll 1s and 6s, right? Sometimes we'll roll lots and lots of combinations, but we'll get that average. If the expected value of students to show up in office hours was, say, 3 during any given hour, some days there'd be nobody, some days there'd be 10 people there, right? So, but on average, we would say we expect 3, okay? So let me share some data with you. I'll just write it out. I've done an experiment with my students of rolling a 6-sided die, and let me make a little table for you. Number of rolls and the mean. So what I did was, I've done it hundreds and hundreds of times now. Well, I've had students do it hundreds of times, right? I'm going to take each student and have them do it 5 times or something, and so I have a lot of rolls. After 20 rolls of the die, I collected data from my student. The average, or the mean, was 3.00, right? Not super close, not terribly far from 3.5. After 50 rolls, we were up to 3.36. And then let's jump a little ahead. 430 rolls later, our average was 3.58, right? So I'm seeing this trend towards the expected value for that roll, right? Again, we're not saying that's exactly what's going to happen, but that's the trend that we should see, right? We know that this is a powerful tool, right? One piece of evidence I have for this is insurance companies. Insurance companies use things like expected value. They compute the cost they expect a person to cost them, right? So if you're getting health insurance and you fit into a whole bunch of categories, you know, based on gender and age and geographic location and education and habits and all this stuff, any bit of information they can collect. With that information, they put you in a category, and they can compute, based on years of data, how much they should expect to spend on you over the course of you being their customer, so they charge you accordingly, right? They want to make money off of you, right? Now, of course, some people have some kind of catastrophic illness and they end up costing a lot more, but then a bunch of other people don't cost them any, or cost them much lower than the expected value. And so on average, right, there's a reason that those companies are profitable, or there's a reason that Las Vegas exists. Every single one of their games has an expected value, right? If you walk up to some kind of electronic game there, they know exactly how often people will win, with what odds, and how much they'll win, and they compute the expected value, and they just charge more than that. And that's all they have to do to make sure that they will make a profit on average. Somebody will walk out winning a jackpot, a whole bunch of other people will walk out losing a bunch of money, and in total, the house will win. Let's look at one more example of this idea. Let me share something different with you for a moment here. This is from an actual state lottery, though I just found the odds on the back of a lottery ticket or online somewhere, I don't remember, from a number of years ago. But so what we're looking at here is a Powerball I don't know the lottery game, so I don't really know what that means, but I know it's a thing. There's something called the Powerball. So this is a Powerball worth $450 million. And I made the random variable W is Powerball winnings after cost, right? So here's all down this column, this first column here. This is our probability distribution for W, these first two columns. So notice what I've done is subtracted the $2 from all of the winnings. So if you win the $450 million jackpot, you actually only win $449,999,998 because you spent $2 to get it, right? And then there's all these other winnings, all of them subtracted $2. This down here represents you buy a ticket and win nothing, and so you've lost $2, right? So now in this column, I've just recorded all the probabilities, right? These are designed by the lottery, right? However they design the game, they can construct odds that they want, right? So you see this massive winning also has a very small probability, right? How many zeros? We see a lot of zeros there, right? And all of these, they're slowly getting larger, but they're still incredibly small probabilities, right? This 2.5% is the largest one besides not winning, right? You have almost 96% chance of not winning, and then you've got another couple percentage, right? If you look below this line and do quick sum in your head, if we say 96%, 2.5, 3.5, now we're down below a percentage. So we're talking about 99% of people would win, less than $5, it looks like. But in any event, these are all of our probabilities. This is this side of this left side of this table is our probability distribution. So over here in this last column, I've multiplied each of the winnings times its probability. So of course, this massive winning times this small probability gives us a much more reasonable number. And then there's a whole bunch of the same thing for all of these, right? So these numbers end up being pretty small. And then there's one down here, the negative $2, which is a very small amount to lose, but almost everybody loses it, right? 96 lose it, and so we multiply, we get this negative 1.92. When you add this all up, our expected value, right, is negative 0.15. In other words, the expectation when you play this game is that you're going to lose 15 cents on average, right? Of course, for an individual, it varies wildly, right? Somebody won that $450 million, I presume. I don't remember the results of this one. I don't even know if that's a game that people win every time, but certainly in many of these things, somebody wins the big jackpot. Some of the people win some of those medium prizes, right? Plenty of people win these prizes up here. But the vast majority lose $2, and there's enough of them that overall the average the lottery takes in was 15 cents per ticket. People lost an average of 15 cents per ticket, right? Or something close to that, right? And so we know this calculation works to some degree because lotteries are money makers for the states that run them. And so this has, we can look back at these records and see how close to these expected values we are. Okay, let's stop that. Let's go back to one more example. Okay, so we're going to compute expected value for something we've seen before. So I want to open up a different set of data. This is something we computed last time. So this is, let's make our, give me 1 second. This is from our experiment where we rolled a four-sided die, or two four-sided die, and added them together to create the probability distribution, okay? So again, I've got a table here. These first two columns are the probability distribution. So you can look back at a previous video to see how we computed that. But this is our variable S. Maybe I'll remind us what S was. S was the sum when rolling two four-sided dice. Okay, so this was the probability distribution for that. So what I want to do now is compute the expected value for this, and I'm going to use our software to do it this time. So what I've got in front of me, I'm just going to type in a little code. So I want to multiply, so I'm doing a formula, and I'm going to multiply, I want to multiply the value in B3 times the value in C3, right? Those are the two, that's the value of S times the probability of S happening, right? I'm just following that formula as before. So I'll hit enter, and we see that first product is 0.125. Instead of typing it in over and over again, I'm just gonna, when you grab this little square here, I'm pulling it all the way down to the bottom. It does the same thing in each cell, but as you move down a cell, it also changes the numbers. If you look up in this upper left-hand corner, B4, C4, maybe I can make this just a little bit bigger. Right, so I copied where it said B3 times C3, it changed it to B4 times C4 as I move down. It does it for all of them. And so we get a quick, product of these values. So the last step is I'm going to sum them together. There's our expected value of X is going to be right here. I'm going to again use, and it's guessing that I want to add up the ones above me, which I do. So I'm adding up those products, and I get an expected value of 5, right? Which we might look here and say that it might be a little bit obvious, right? 5 was the middle value, and everything on either side of it had equal probabilities, right? 8 and 2 had the same probabilities, 3 and 7 had the same probabilities, 4 and 6 had the same probabilities. So there's kind of symmetry to this situation. And so the expected value falls right in the middle there. Okay, so I think that's it for expected value. This is a pretty big concept, and we'll use expected value a lot. And it's one of the tools that we have, right? When we're using probability to actually do things, right? The things I actually mentioned already, I think, are pretty good examples. If you're trying to insure somebody for driving, you want to know what you expect to spend on them. I'm saying it in a careless way. We're not really thinking what we would expect to spend on them. What we would expect to spend on thousands of people like them on average, knowing that for each individual, many different things would happen, right? So in any event, that's it for this one. Thanks, everybody. I will see you next time.